All right, here you go. What are y'all chuckling about?
This thing linked.
Oh. Where did you get it?
There wasn't a cup. Yeah, no, I'll go get it.
Just make a mess. All right, everybody there? All right, we're doing better. Yes, it's C. Okay, so give me some random numbers now. So where does the aromatic ring come? 7-ish, and ish is good, to know ish. Okay, just be like around there. Okay, where do you think that's gonna come? Well, it's affected by how many things? 2. You got it next to a benzene ring and next to a carbonyl. If it was just one of them, it's 2 to 3. So because it's affected by 2, it's probably more around 3. Maybe even a little farther than 3. So I'm going to go about 3. Okay, where does that come? That was the big winner. It's what kind of proton? Aldehyde, right? What is going on with mine? Watch. Okay, 9 to 10. Okay, what comes above 10? Carboxylic acid is like 10 to 12. Okay? Nobody picked D. I'm considering that a good sign right now. Okay, so we were working on these. Okay? Did anybody get anything for the next one? C2H3Cl3. Want all of your hydrogens to be the same kind. Okay? So how can you have 3 hydrogens and they're all the same? It's a puzzle. It's a puzzle. Work the pieces. You only have 2 carbons. At least it's not as bad as that one. It had 8. Okay. So start, if nothing else, draw a structure that fits that formula. That will kind of get your brain thinking. Okay. You'll know when you do that, you'll know if it has any double bonds, or if it's all single bonds, or if it has a triple bond. Okay, you'll know that once you draw a structure that fits the formula. And all the carbons have their 8 octets. Okay? So like, somebody throw me a possibility and I'll draw it up here and we'll look at it and see if you think it's right. What should we do? Okay, and then?
Then it's the
Uh-huh.
chlorine off of that.
Okay, so all of these are the same kind. Why is the shift 2.7? Because there's 3 chlorines over there. Okay, good. Maybe we should have done that one first. All right, how about C12H18? Remember, we only want 1 peak. So that means we have to get all 18 of these H's to be identical. How did we do it on the last one? On the first one? For branches, right? sort of like draw something down. See if you can make something that fits the formula, even if they're not all the same kind. Because like I said, it's going to tell you something about the structure. Did you have this page on your deal? Let me see what you have for the next page. I have another one. I have these, but I must have added stuff last year. I didn't remember. All right, how you doing on this one? All right, I tell you what, I'm going to skip it. Because I'm trying to make you work for us. And so on Wednesday, because I'm mean like that. Okay. All right, look at this one. There's isomeric compounds that have the molecular formula C4H9Cl. So if you have C4H9Cl, and you're going to draw all the possible isomers, okay? Choose the one having a proton NMR spectrum that has only one peak, several peaks, including a doublet at 3.4, several peaks, including a triplet at 3.5, several peaks, including two distinct 3-proton signals, and it gives you that. Okay, so in other words, there's going to be one structure that fits each of these. Okay, so starting with C4H9Cl, can you draw structures that fit that formula? Okay, and give me one. Don't worry about that stuff yet. Just draw me a structure. I'll give you here. It's a puzzle. All it is a puzzle. Okay, so do we have a structure that fits C4H9Cl yet? What did you write? What are you going to do? See what? Can Cl can only have how many bonds? One. So it can be off a carbon that's in the middle. No, just draw me a structure, and then we'll go figure out if it fits one though.
Just put it on.
Put it on the end. Okay. 1, 2, 3. Okay. So how many kinds of hydrogens does that one have?
4 carbons.
Oh,
I started to say, yeah, I was like,
my bad.
I was like, oh no, we don't have hydrogens.
Okay. So how many kinds of hydrogens should that one? 4, right? Every one of them is different. This one, this one, this one. These two in the middle are not the same. They're only the same if the molecule is totally symmetrical. Okay, it's not. It changes the electronics around those hydrogens. Okay, give me another one.
Branch it off the second one.
Okay.
Oh, I'm sorry, I meant the Cl. But that works too, I think.
Okay, so what's another one? When we're, you want me to move the chlorine to the second one? You said branch, so I thought of the other kind of branch. what else we do? There's more.
It's like, for instance, doing central carbon for 3 CH3.
Nana. Okay, all right. I'm going to do this just so there's a lower end one here. All right, are there any other ones? Or are these the only 4?
You do two, like two,
Okay, so what do you want me to do?
like branch and then branch the CO.
Okay,
So like CH2 with the methyl. Okay, yeah, CH2 and then a Cl. Oh no, this is like a CH2. I don't know how to like work this. Okay, so CH2 connected to another CH2.
yeah, you only have 4 carbons. So if you put a CH3 here and a chlorine here, that's this one.
That's your.
Right?
So can you? No, it's the same thing.
I think these are the only. Okay. You're.
It was going to end up.
Sometimes you have to draw them down and look at them and go, oh, that's the same thing. I think those are the only. Okay. All right. Now, which one contains only a single peak? That one does, right? All 3 of these are the same. Remember that makes them identical. So that one's AKA T-butyl chloride. Didn't you make that one? Yeah, like didn't you shake it in stuff off that way? I thought you did. Okay, several peaks, including a doublet at 3.4. What are you thinking? Which one of these would have a doublet at 3.4? Okay, so we use this one, so I'm going to put a little check by. You know it ain't that. Which one would have a doublet at 3.4? So what does that mean, a doublet? It means it has how many neighbors? 1. Remember that it's neighbors plus 1 give you the splitting. Okay, so which ones off there have the possibility of a doublet? The bottom 2, right? Because this has 1 neighbor and these have 1 neighbor. And this one has 1 neighbor. How many neighbors does that one have? 4, right? Okay. All right. So which one do you think would be shifted down to 3.4? What is doing the shifting on this? The chlorine is. So which one has a doublet that's by the chlorine? Which one do you think?
So would it not? Does it not get like?
It does if you're right close to it. That's why it's down to over 3.
So it's like really high.
Yeah. This one?
Which one?
But that would mean this one. This is the doublet. Do you think this doublet is at over 3?
No, it's not.
Or this doublet? It's this one because this one is next to the chlorine. So it shifted farther. Okay? It says several peaks. It's not saying it's the only peak. That's all they're giving you. This is the doublet at 3.4. Okay, who will have a triplet at 3.5? We will have a triplet at 3.5.
Well,
The bottom one, where's the triplet? This one's going to be, let's do all the splitting. What's this one going to be? What? Has how many neighbors? 2 plus 1 is? Okay, this one is how many neighbors? 4, so I'm going to write M. This one is how many neighbors? 5, so I'm going to write M. What's M for? Multiply. Okay. All right, this one is how many neighbors? 1, so it will be a, okay, so who has a triplet? Is there going to be a triplet at 3.5? Who's going to be at 3 over 3? This one is, right? Okay. We didn't mess up, did we? What is the splitting of this one? What's the splitting of this one? How many neighbors does that CH have? 8. Super multiplet. Okay. What about these guys? So it's going to be a doublet. Okay. What do we have up here? What's this splitting? Okay, which one will have a triplet at 3.5? The one on the top. Why is it at 3.5? Because it's next to the chlorine. Trying to decide if I still missed one, but I don't. No, every time in my mind, I'm moving things around, I come up with another one that's up there. Okay, so maybe these are the 4. Several peaks, including 2 distinct 3-proton signals. Okay, so what does that mean? 3-proton signals. 3 hydrogens, that's the integration value. Okay, one of them is a triplet at 1, and the other is a doublet at 1.5. So notice that these aren't shifted as far as these. So what does that tell you about the chlorine? It's not directly attached to them, which makes sense because if you had a methyl and a chlorine, that would be the compound. Couldn't have 4 carbons. Okay, so who has a triplet at 1? Okay, and who has a doublet at 1.5? Why is this one a little farther downfield than that one? It's closer to the chlorine. Remember, the effect drops off with distance. Okay, so this is the bottom one. Let's see if I can write it on here. So it'll be on your slides. Okay. It's a puzzle. It's a puzzle. There's going to be puzzles on the test. You're going to have to solve them. Okay, so you're going to have to be writing structures and figuring. I can give you extra scratch paper. Like usually this is the test that people use extra scratch paper. All right, so here is an unknown. All you get is C9H12. Now, is this on your deal? Amen. Okay. Because I want you to be able to write on it and stuff. Okay, so when you first look at the spectrum, what is the first thing that you see? Does anybody see something and go, oh, I know what that is? What?
We're just trying to find slides.
Oh, did you find it? Okay. When you look at that spectrum, what can you tell me about the molecule besides its organic? It's a ring. What kind of ring? What kind of ring do you think it is? A what? Should I draw a pentagon? What? A benzene ring. Okay, what is the clue for that? Right here. Okay, that's your clue that it's a benzene ring. Okay, because you have peaks at 7. If you just had a cyclohexane ring, way upfield. Okay? Okay. Now, can you tell me how substituted do you think the benzene ring is? Is it substitute 1 time, 2 times, 3 times?
That's 3.
Okay, we have 3 extra carbons. Okay, what else? Okay, there's another clue up there. What is this little number? How many what? How many protons? You'll notice that. Here's a 2, here's a 2, and here's a 3. Notice that they add up to 12. So we don't have to use the ruler yet to figure it out. Okay, what does the 5 tell you? There's 5 hydrogen on the benzene ring. That's right. Okay, notice 1, 2, 3, 4, 5. So how substituted is it? 1. Okay, so I'll draw a little squiggle or something so nobody thinks that's a methyl. Okay. All right, so what you're going to do is you're going to figure out the pieces. Okay, then you worry about putting the pieces together to make the whole structure. And last but not least, always check your structure and make sure you fit the formula. Okay, if you're working out a puzzle, it's really easy to throw in an extra carbon. Okay, it's just really easy to do that and not catch that you did it. So check that before you turn your test in. All right, so we got a benzene ring. Look, I can give you a point already. Okay, partial credit. All right, now, what can you tell me about these guys? Okay. Well, do you see the blow-ups? Can you tell which blow-up goes to which one? How are you going to tell that? Here, I'll switch colors. That's how I'm going to tell. Okay, so this, who does this blow-up go to? Yeah, because you look at the scale underneath, okay? So which one is around 2.5? That's this one. So I'm going to write red. This is the red one. Okay, so what can you tell me about neighbors? How many neighbors do you think it has?
2.
Yeah, 2. Okay, I'd go with 2. 2 is a good number. Okay, where is this one? This can be the green one. Which one do you think it is over here? The middle one. That's the green one. Okay, how many neighbors do you think it has? That's why the blow up is there, to help you, not confuse you. How many? 5. Okay, how did you get 5? You counted all those little peaks, and how many did you get? 6. Okay, all right, so the last one, we'll just have to make it purple. Okay, is this one, and it had better be this one. You didn't like purple, I guess. What's wrong with that? Okay, what can you tell me about the number of hydrogens of each one of those, that each one of those peaks are? This one is 2. This one is, and the purple one is 3. Okay, so what would that lead you to think? CH2, and then what? And then okay, can you tell me who's next to who? Okay, the first CH2 is next to the next one, and then this is next to that one. Okay, does that fit the splitting? Notice that this has 2 neighbors. This has 5 neighbors, and that one has 2 neighbors. Okay, so now look at the shift. The shift of the red one is farther downfield, so something has to be shifting it. Okay, look at how many carbons we've used in our structure. We use 6, 7, 8, 9. Do we have any left? No. So what do you think we're going to do to draw the whole picture? We're going to put them together, okay? Okay, the answer is propylbenzene. I guess I didn't draw the structure, whatever. Thought I'd selected that. Okay, so here's my benzene ring, and it has CH2, CH2, CH3. Remember that this carbon right here, there's no hydrogens on it, right? So we're not adding another neighbor to that CH2. It's still going to be that nice little pretty triplet. Okay. Okay. How you feel about that one? Okay. It's working the puzzles. All right, let's work another one. C5H10O. Okay, C5H10O. All right, when you look at this one, what do you see? Anything in particular stick out at you? What do you see when you look at that spectrum? How many kinds of hydrogen are there? 2. How many hydrogens we got total? 10. So what does that take? You gotta have some symmetry, some same things. Okay. Okay, is there a benzene ring in this one? No. Okay, what's your clue that there's no benzene ring? There's no bunch of peaks over here at 7. Okay, what else is your clue that it's not a benzene ring? You only got what? 5 carbons. Oh, draw benzene rings if there's only 5 carbons. It takes at least 6, right? Okay. You'd be surprised how logic goes out the window during the test. Okay, I'm serious, so don't feel bad. Yeah, I'm trying to keep you from doing these things. All right, so what can you tell me over here? This is, oh, here, well, I guess we're going to use green. This one is this one. Okay, what is the splitting of the green one? 1, 2, 3, 4. It's that's a Q. Does that look like a Q? It's a funny font. Okay, so how many neighbors does that one have? 3. 3 neighbors. Okay. This one is obviously the other one. I just don't want you to make the mistake of going, this one is this one, because it's closest. Okay, so look at the numbers. This tends to be how they are in your book. All right, so the purple one is a what splitting pattern? Triplet. How many neighbors does that guy have? 2. Okay. How many hydrogens do you think are under each peak? Is this one 2 and this one 3? No, because it doesn't add up to 10. How are we going to get it to add up to 10? What are we going to have to do? 5 times what is 10? 2. Okay, I know higher math in organic chemistry. All right, so we're going to double these. So this is going to be 4, and this one's going to be 6. Those 4 hydrogens only still have 3 neighbors. And the 6 hydrogens still only have 2. How can we have 3 with 2 and 2 with 3? What's the structural feature that we're looking at? Yes, a lot. Because that's the smallest whole number ratio. Sometimes it's like that last one, it was even. Sometimes you won't even get these. You'll have to do the measuring. Okay, we're going to probably do one with that. All right, so how could you have 2 or something that's split by 3 and something that's split by 2? What do they got to be? A what and a what? There's your clue. CH3, CH2. Okay? And because that one's 4 hydrogen and that one's 6 hydrogen, how many of those ethyls do you have to have? 2. And they have to be the same. Okay? So when you put this together, you got to keep them the same. Okay? What's left from your formula? An O, is that all? And a C. Any ideas?
Down to the ethyl.
Mm-hmm. Look at there. All right. Do you see why these are the same? The 2 methyls on the end and the 2 CH2s in the middle. Okay. Now look at the shift. If you're next to a carbonyl, you should be shifted above 2. It's usually 2 to 3. Okay. Looky here. That's where the shift is. So something's affecting it. All that was left was a C and an O. The only way you could put that together so that it would be symmetrical and that last carbon will have its 4 bonds, okay, is a carbonyl. Okay, what is the other thing that could be done to tell you that there is a carbonyl there? Did you, what? Run an IR. Okay, that's why we run IRs, to show where carbonyls. So there's not going to be any IRs on this test, but there will be IRs on the next test. Okay, so FYI. But that is like a super easy clue to look at the IR and go, there's the carbonyl. Okay, I got a carbonyl. Okay, that'll help you. But you can do them without the IRs. Okay, look at this one. Okay, any exciting things out of this one? What are you thinking? Bob? Okay, so you look at this one, we got C9H10O2. So what can you tell me? Anything about the structure? There isn't? Okay, well look at this. What are these? 7 to 8. That's a benzene ring.
I thought benzene ring can only be on.
No. Oh, it's 7-ish. 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 Okay. Yeah, no, it's not that set in stone. It's going to vary depending on what's attached to that benzene. Okay, how substituted do y'all think the benzene ring is? All I'm going to draw you right now is a benzene ring. How substituted do you think it is? Look at those little green numbers. It's kind of like little green aliens. What do you think? 1. Why did you get 1? Because you want 2 plus 1 plus 2 is 5. Okay? Don't just see the 2 and go, oh, it's 3 substituted. All right, what have we got down here? What is this? What is this? It's what splitting. It's a quartet, so it has how many neighbors? Quartet, 3 neighbors. Okay? What about this one? It's a triplet. It has how many neighbors? Neighbors. Notice that this time our little green numbers added up to 10. More kinds you have, the more likely it's going to be the same. Last time we had to double them. Okay, so how can you have a quartet and a triplet? What is it going to have to be? What is my pieces? Oh, an ethyl. another CH2, CH3. Okay, so I've got two pieces of my structure right now. Okay, what do I have left in my formula? All right, well, I used C6, okay, 7, 8. So I've used up C8. How many hydrogens have I used? Well, I used 1, 2, 3, 4, 5. Plus 5 is 10. So what do I have left? CO2. Any ideas? Remember, everybody still has to meet their correct valence and all that good stuff. Okay, so what do you think? I'm going to switch to black. How can I, what do you want me to do? If I take the benzene ring and I stick the ethyl on it, do you see that that's not right? Okay, and there's no place then to put the CO2. So where does the CO2 have to go? In between them, right? Okay, so how do you want me to do it? Here is your first piece. Here's your benzene ring, and then what do you want me to put?
An oxygen.
Okay, and then a?
Carbon with a double bond and oxygen.
Okay, and then what? CH2, CH3. What kind of compound is that? An ester, right? Okay. Okay, now look at your shift. Who should be, aside from the benzene, who should be the farther downfield one? The CH2, right? Okay, it's next to a carbonyl, so it should be where? 2 to 3. It's above 4. How did it get above 4?
Directly attached to that.
Yes. When you figure out that it's an ester, there's going to always be two possibilities, and you have to figure out which one is which one is right. Okay, so you see that this O here is on the CH2. That's going to shift it way far down. Okay, and this O is on the benzene ring. Okay, so this CH2 isn't going to be shifted as far. 4 is pretty far. Okay. Okay, so it's this one. It's not this one. Okay, does everybody see the two possibilities? And then you have to figure out which one it is. Look at who is shifted further. That's how you can tell which is attached to the O. Oh, wait. I think, let's see what I have under here. Oh, I just have the structure. Okay. Any questions on that one? How are you feeling about it? Any better? I mean, I feel like there's only 2 days. All right, look at the next one. All right, we're going to do some numbers. Anybody look at this one and see anything? Yeah. Woohoo! Go, Caitlin. Caitlin's going to be the benzene girl. Okay, any idea how substituted it is? And what? Somebody else said something. An aldehyde. Do you remember what an aldehyde is? Yeah, CHO. Okay. Oh, we got 2 pieces already. Holy cow. All right, now what do we have left? We have this. All right, so what you need to do next is figure out what the hydrogens are under the peaks. Okay, so you're going to take this little ruler here, and you may bring your ruler to the top. Okay. Can you measure for me, Stacy? Oh, wow, it's really little. Yours looks bigger. He printed it this way. Let's use this. Okay, so first of all, I want you to know where we're going to measure. We're going to measure from here to here, okay? And we're going to measure from here to here. Typically, you measure flat line to flat line, okay? And here, we're going to measure from here to here. I didn't draw that top line really good. All right, so here, measure them and tell me what they are. You can do it, Jeremy.
Like what I did.
You can, I would use millimeters. It's easier when it's small like that. Okay, tell me how many millimeters. I'm going to write them all down.
Centimeters.
What?
Is this centimeter?
One side is inches and one side is millimeters.
We golden. One.
Okay. All right, so what am I getting?
Yep.
What did he say? 1 centimeter?
Yep.
Okay.
So 10.
All right, what's the next one?
35.
35 centimeters?
No, millimeters.
Okay, you got to do it all in the same unit.
3.5.
All right.
And 1.4.
Okay, and you sure this one is 1?
Yes.
All right. All right. So what?
Want to verify?
No, it could be printed. Okay. All right. So now we're going to add them all up. So we get 4.9, 5.9. So I have 5.9 centimeters. Okay. Now I'm going to divide by how many hydrogens? So how many centimeters per hydrogen? Surely somebody's done it already by now. Y'all are way faster than me. All right, I get 0.7375. You get that? All right. And the unit is centimeters per hydrogen. Okay, so what do I got to do to figure out how many hydrogen? I'm going to take 1 divided by 0.7375. I get 1.3. I'm just going to write 1. Okay, 3.5 divided by 0.7375, and I get 4.7. Okay, 1.4 divided by 0.7375, and I get 0.5. Do it right? Yeah, 1.89. I must put it in wrong. I'm like, okay, so what do you think they are for hydrogen? Like you got around. So this is going to be probably 2. This one is going to be 5. And this one is going to be 1. Okay, so what is that 5 hydrogens for the benzene tell you? It's monosubstitute. That's like a phenomenal clue. All right, now we're drawing us the line. So we've got this, and what's left? What's left over here between at 3.5? We've got 2 hydrogens at 3.5, and it's what can you tell me about the splitting of the CH2? Do you think they're splitting? It kind of looks like a double, doesn't it? What can you tell me about this one over here? It's kind of weird looking too. So what does that tell you? The CH of the aldehyde and the CH2 are next to each other. Remember, the CH of the aldehyde doesn't always split really good. It's like weird because of that carbonyl. So how am I going to put these pieces together to come up with structure? I'm going to have my CH2 attached to the benzene ring, and then the aldehyde. Okay, notice where the shift is for that CH2. It's affected by the carbonyl and the benzene ring. So it's at 3.5. Okay, do we fit the formula? Count the hydrogen. Okay, yeah. Okay, IR spectrum on the next slide. Okay, so I'm going to show it to you, even though we're not doing it. And I want you to see that right here is your CH of the aldehyde. And here is your carbonyl. Did you talk about aldehydes? IRs? Okay, that's the only way to tell the difference between an aldehyde and a ketone on an IR is by looking for that doublet. Okay, let's see what I wrote over here. I just wrote the structure. Okay, go to the next one. Okay, this is the IR for the next one. We'll just go to the next one. Okay, and what can you tell me about it? Right on.
Benzene ring.
Benzene ring. She's going for that point there every time. All right, benzene ring.
If there's a ring,
There better be one. Is that what you're
I'll
telling me?
be mad if there's not one. I'm saying.
You can say no benzene ring. Okay, does the benzene ring fit our formula? We got enough carbons? Yeah, okay. All right. What else can you tell me? Can you tell me how substituted the benzene ring is? 2. How are you getting 2? Looky there. Can you tell me, so how are the 2? Are they next to each other? Are they opposite? Are they one away? What? Yes. What was that called? Para. It's called para substitution. And how do you know that? Because you have this doublet of doublets. And they can be skewed. Okay, they can be closer together or farther apart, depending on what's attached to them. So now this benzene ring isn't on an end, it's in the middle, right? Okay, so what else have I got? What is at 3 point whatever? 3.8. What do you think this is? It's 3 hydrogens. What can you tell me? What's it splitting? It doesn't have any. So what does it tell you about its neighbors? No neighbors. Singlet, no neighbors. So it don't look like an oxygen planet. What can you tell me about this one? Does that have neighbors? It's another singlet, no neighbors. So how am I going to put that together? What is my structural feature? How can I have 3 hydrogens that are a singlet? They're attached to the same carbon. How can I have 3 hydrogens that are a singlet? They're attached to the same carbon. Okay. Now, what is left in my formula up there?
One of the analysis further down.
Right. So here's my benzene ring. I'm going to have a methyl on one side, and on the other side, I'm going to have OCH3. Okay, 6, 7, 8, right? We have 8 carbons. Notice there's no carbonyl on this one. Okay, so don't see O and think carbonyl. Okay. Are you getting it? The only way you're going to get better, y'all, is to practice. Practice, practice, practice. Seriously. All right, understand there's a big immunology test today, too. Good luck. Y'all do good.